One of us new entry this morning.
Is there a pointer?
What? Yeah.
Yeah, this can work well.
Oh, okay.
Center button.
Great.
Should we give another bit maybe? Yeah.
Yeah. Let's stand back from the let's just let them have a run at it. People find it difficult to deal with their disappointment. I think.
So I think before that, a couple of things. First, there are 9 people signed up to go to LIGO Hanford on Saturday, this Saturday. We'll give you the exact time of departure, etc. In a couple of days. But tentatively, we are leaving around 9 o'clock in the morning, and we should be back by, I guess, 8-ish. Okay, maybe even sooner. If you didn't have a chance to sign up and you would like to go, feel free to meet me after the talk. The second announcement is, we are planning to have the morning talk this Friday at an earlier time, namely at 9:30. So the talk is by Professor Hubert, who isn't here yet, but I think he is agreeable to that shift. Does anybody strongly object to that change of time? So having the talk on Friday, not at 11, but at 9:30 in the morning, same place. Will you be able to attend it? Okay, vigorous shaking of hands. Okay. Okay, so then I think that's from them. So, okay, this afternoon we have David Neilsen, who is going to talk about recent work on binary neutron stars and beyond.
Okay, thank you. So I kind of chose a vague title because I wasn't sure exactly what I want to talk about, but I kind of was influenced by the discussion yesterday that I attended as I've here for this week, and of course I'm talking about binary neutron stars, and this is kind of a nice graphic that shows the overall scenario that we're looking at. We have some type of an in-spiral, a merger, and then possible end states of either, if I have very massive stars, immediately formation of a black hole, but more likely formation of a hypermassive neutron star that can settle into, again, one of these two end states of either a single neutron star or a black hole. Yesterday, Steve talked about some of the work that we've done with leakage, and I'm not going to extend that a little bit. But there was some interest in the work that we've done with electromagnetic counterparts, so I'd like to go straight to that. This work kind of began a while ago with interest with the Blandford-Znajek process. So basically, this process has been around for many years, but the basic idea here is that when I have a spinning black hole and an external magnetic field, the rotation of the black hole will drag this field lines around, and there will be a production of a thin diffuse plasma. I mean, essentially the voltages across these field lines are very, very high, 10 to the 20 volts, something like that. And as these field lines become twisted, they break and reconnect, and this is a source of energy of radiation. And it was, has been considered it's the expected model for the power of quasars and other jets from spinning black holes. We've done some early work with black holes and electrovacuum, and then in looking at this further, so we talked about in the force-free limits of electromagnetism. This is where I have strong magnetic fields and a very thin plasma diffuse plasma, where essentially the inertial forces of the plasma can be ignored. And by looking at both binaries and single boosted black holes, this is a single, this is a binary configuration here. But kind of phenomenologically, we found that the luminosity could be broken into two components. There was a luminosity that comes from the spinning black hole that was known from the Blandford-Znajek process, which depends on the magnetic field squared as they do, and also on the rotation rate or rotation frequency of the horizon, and a component that comes from having a velocity, a boost with respect to the field, sources of the field, that depends on the velocity squared. And so here was in case where we had a single boosted black hole, you boost the black hole and look at the velocity as a function, or the luminosity as a function of the velocity here.
The binaries of the single black hole? Or?
Yes.
Yes.
Yeah.
It's not for binaries, just a single black hole moving?
That's a single black hole moving, yes. But of course the same thing will happen in a binary. The same, both effects will be there for a binary. And then to extend this, as we talked about yesterday, this is kind of there seemed to be some interest in the resistive MHD model. Just quickly, when you're now trying to take this and say, okay, now what happens when we put a neutron star in the external field? So we've looked at the black hole first, now thinking about the neutron star. The difficulty, of course, is that you have two very different regimes. You have the regime of the interior of the star where you have very high density, very high conductivity. You're basically in the MHD limit. And then exterior to the star, you have the magnetosphere, and you have very strong magnetic fields. You have, again, the diffuse plasma that is inertially and gravitationally unimportant, but reacts, or the fields are strong there. And this is the force-free limit of electromagnetism. What we'd like is something that kind of smoothly goes between these two regimes and can also account for finite conductivities. The resistive MHD model can do this. In the resistive MHD model, we have the fluid equations as expected, and in addition, the full Maxwell equations. The two sets of equations are coupled through the choice of the current. And the choice of the current is kind of the question that comes up here. I was going to put more details here, but it becomes quickly, a kind of a mess. But basically, as Niels was pointing out yesterday, you begin with a form of the conductivity in space-time, and then you kind of look at that and you say, well, if I could, maybe drop a couple of these terms here that don't quite fit, then I get something that looks like what I expect in FFE. And if I, have another term here that becomes important, then I get something that looks like the MHD condition. And so while a couple of these terms are dropped, what remains behind and can be you have some functional form that then you can put parameters on to smoothly vary between one and the other. So that's my hand-waving explanation of that. Like I said, it's kind of messy to put all up just on slides. But with this kind of phenomenologically chosen current, it's a current that has Ohm's law in it, as you would expect, and it also has some anisotropic terms that come from the magnetic field, but it does not have all of them. With this choice of a current, you can then say, as a function of the density, vary between the MHD and the FFE regimes.
Can I ask you something? Is it as low conductivity, or is it like the limit of ideal force-free electrodynamics, or is it like?
Oh, I think I should have. I actually didn't want to talk about conductivity. I just wanted to say it had low density and inertially. Anyway. Yeah, that's a mistake. So we looked at, again, a single star boosted in an exterior field. In this particular set of pictures, the way what's being plotted here is 4 scenarios. Well, there are 8 here, but 4 different field strengths. BC, so here we have a ratio. BZ is the strength of the exterior field. BC is the magnitude of the field on the surface of the star. And by looking at these, 4 different magnitudes here, you get kind of a picture of what's going on. In the top row, this is where the field is aligned with the star. I'm sorry, the field of the star is aligned with the external field. And the bottom row, they are anti-aligned. And you can obviously see the changes here, especially at the strong field strengths. You can see how the field of the star has distorted the exterior field. In limits, you can come up with some guesses as to what should happen. It turns out that this quantity that I was showing you, BC over BZ, you can show that we would guess that the luminosity would go as that quantity to about the 2/3 power. And by measuring the luminosity from this scenario after it's kind of settled down to steady state, that's what's seen. The black line is where the fields are anti-aligned, and the red line is where they're aligned. And again, given the different field configurations, it's not, it makes sense that the anti-aligned field has stronger emission. And again, the v squared dependence on velocity.
In the left panel, what is it you're measuring? I mean, this is a boosted star, or is it a stationary star?
It is a boosted star, but in this case, they are all the same boost. And it's the magnetic field that is varied. I didn't mean to do that, whatever that is. Anyway, hopefully that will go away. So Steve talked about the work that we had done with then going on to work with the binary. And just as a reminder here, he looked at different scenarios where one of the stars was basically unmagnetized, that's the small u. One of the stars is strongly magnetized, that's the capital letters. And then I have configurations where the fields of each star are aligned or perpendicular to the orbital angular momentum vector, or the normal to the plane. And get these pictures like this. One thing that Steve showed or mentioned but didn't talk about was in the case where I have the one star perpendicular and the other one up. The field lines become 3-dimensional. They go through the equatorial plane. In this particular picture, the equatorial plane is there. It's plotted. It's kind of opaque. And so when you see a color change here or intensity of the color change, that's where the lines are going into the plane or coming back out as it goes one way or the other. He showed this picture with the different modulations in the Poynting flux. Here is so looking at a sphere that's, I don't remember exactly how far away the sphere is from the binary, center of the binary, but this is the Poynting flux mapped onto the sphere, so you can see the different patterns in the radiation. They are time dependent, and I forgot to label these. This is the well, I think they're on the next slide here. This is the more, well, that's nice. This is kind of shows you what's happening in time. Basically, the question here is how much is the radiation collimated? To answer that question, we basically looked at a couple different quantities here. So we're looking at the amount of radiation with the blue line that's between 0 and 30 degrees averaged over the sphere, and the amount of radiation between, say, 30 and 60 and 90 degrees, so to the plane. Where the blue line is significantly higher, then you would expect more collimated radiation. where they're all roughly the same, or no variation, it would be more radiation that's uncollimated. These are the cases where the fields of the two stars are aligned or anti-aligned, so they're up or down or something like that. And then in these cases, one of the stars is perpendicular and the other one is up or perpendicular, anti-aligned or something like that. And the interesting thing here is there's, of course, much more time dependence here in these configurations where one of the stars is perpendicular. But as Steve mentioned, when you have the one star perpendicular, you have more breaking and of the magnetic field lines. Okay, I'm going to kind of change topics now and talk a little bit about the Kelvin-Helmholtz instability. So in the talk yesterday by Ken today, we had a nice presentation of that, and this is something that we had also been looking at, but we're still kind of in the process of doing. Just as a reminder, there have been some local simulations at trying to measure the growth of fields and the saturation point in relativistic fluids. So here are a couple, and basically results are the average fields are saturating somewhere around 10 to the 15, 10 to the 16 Gauss using ideal gas, or in this case a Shin equation of state, so a finite temperature equation of state. And we wanted to see if we could do something like that with our code, and using now a global simulation with binary neutron stars. We chose two 1.3 solar mass stars in a binary. Radius is about 10 kilometers. We put them very close together. We were just, because we're doing this with very high resolution, we want them to merge as soon as possible and have small grids here. The resolutions that we were looking at were 300, 150, and 75 meters. This is a picture of, basically the color mapping is B squared here with the velocity field arrows. You can see kind of these rolls that you expect here in the Kelvin-Helmholtz type stability. And I've also plotted the vorticity, but anyway. So we are still working on the highest resolution, the 75 meter one. For the other two, we're basically seeing a jump of about an order of magnitude in the field strength, and then some additional growth with compression and such, but nothing that really looks like, nothing more than this, about 1 order of magnitude growth. If I looked at the slides from yesterday correctly, then the green line here would correspond to Kenta's, I think, coarsest resolution roughly. Is that right? And that's where you also saw about an order of magnitude or so growth in the field. And anyway, so we're hoping that with the blue line, which corresponds to close to his finest resolution, that we'll see further growth in that field there. But that's something that we're still working on and not yet finished with.
This is ideal MHD.
Yes, this is ideal MHD. Convergence only in the sense of having done these runs. Or what do you mean with the convergence?
I mean to see if you are in the convergence regime for if you have a Kelvin-Helmholtz instability, to see like for the different resolutions if you are.
No, it's still going on. So I mean, we would need yet another resolution to make sure that we're converging to the saturation point. Is that what you're? Yeah, so it's something that we're still working on.
These are going to be like 10 million CPU hours?
Well, we're putting them close together, and anyway, well, it's taken quite a lot. It really burns through an allocation. Okay, and that kind of brings me to the last topic that I wanted to talk about, was high performance computing. So we talked about, some of these calculations we were interested in and we're interested in result, but actually performing them takes a lot of time, and it's not always easy to get the time that you want. Sometimes anyway, there can be different time scales involved. Sometimes it's theoretically feasible to do this if someone would just give me the time, and other times it just becomes much harder. And in thinking and looking at this, especially as we want to add more physics to the codes, which of course makes them is even more demanding computationally, it's good to kind of keep an eye on what the future of high-performance computing will look like. This is from a quote from a study that was done just last November. It was a kind of a white paper study on what's the computing going to look like in the year 2030, and and this was actually done for NASA Langley, and so the question was basically what should NASA do and plan for as they look for their computing needs in the next 15 years or so. And the quote is basically, HPC hardware is at the cusp of a paradigm shift that will require significantly new algorithms and software in order to exploit emerging hardware capabilities. And that's because basically computers are changing. As we want to go from the petascale era to the exascale era, which is another factor of 1,000, computer architecture will have to change. Basically the game of increasing clock speeds and decreasing die sizes is almost at the end of what it can do, both from fundamental physics limits that are being approached, and also just the power required to run these. The power goes up with the processor goes up with the cube of the clock rate. So it is a game that will end with kind of the current architecture. So what you do if you want to increase computers by computation speeds by another factor of 1,000, you look at very heterogeneous networks where we have different types of hardware accelerators that can handle lots of very lightweight hardware threads to do certain parts of the computation extremely fast or quickly. And there are kind of two things on the market right now. One is the Intel FICO processors, which work on one model of, they're basically distinguished by, well, let me go back and say, in both of these models here, we have basically a main CPU, and then we have small devices, either a GPU or a coprocessor chip, that are optimized for, say, floating point operations. They're distinguished by basically by cache coherency. Exactly what the future computers will look like, of course, is still unknown. But we can see, but no matter which one comes out ahead, the basic programming methodologies are going to be roughly the same. Where, the way that you write code that's really optimized for a PHY or really optimized for a GPU is quite similar. As an example of two machines, this is the machine that we're currently running and doing some tests on. It's Big Red 2 at Indiana. Because this is recorded, or maybe I won't say one or two things about it, but it's basically a big machine, kind of standard, with Opteron cores, but they've also put on a whole bunch of GPUs, NVIDIA K20s, which each one of them has almost 2,500 cores, floating point cores. This is kind of a new architecture that's coming out just this year, this fall, will be available. It's basically a box that you put in a rack. It's got 8 ARM 64-bit processors, 2 NVIDIA K20s, which are these big black boxes here. These are basically what power your cell phones and iPads or whatever, tablets. So you've got these very small, lightweight processors, RISC processors, that draw very little power, but are there to essentially run these big floating point units here. So this is more the model that I think we'll see as we go into the future. What's different about them? Well, a CPU basically has a lot of control of fancy logic code. I'm not a computer architect, so this is my hand-waving explanation and little picture that basically tells me that in a CPU I have a lot of very sophisticated control logic to make sure things go quickly, and then I have a lot of cache on hand because as I'm doing calculations, of course I need to bring things in and out of memory, and cache allows me to speed that up. What's different on a GPU is, it's kind of hard to see, but these little green boxes here represent the floating point units, and a GPU these are all floating point units. You can see they have very little cache control. I think of them as being small, stupid guys that really know how to calculate numbers, but they're not very sophisticated as far as logical control. And that's basically the idea. My laptop sitting here has 4 cores in it, and I think 450 cores in the GPU. So there's a big difference between what is available in the GPU and what's available on the CPU. As I said, they're kind of stupid, or at least that's where I think of them, and that means that the programming then is not necessarily simple to do. You have to, where in C, where you're just writing standard C code that'll execute on the CPU, you can write any valid C program and it will just automatically work right. On the GPU, you have to be a little bit more careful to make sure that it both works and works efficiently. The basic idea is you have in your box, you have your CPUs, and they can interact with RAM and memory and stuff over here. But the difficulty in using this, and what's kind of is that the connection between the CPU and the GPU is quite slow. It's very slow, and that represents a significant bottleneck. And kind of the traditional model has been, well, do all your coding for the CPU. That's where we're used to doing things, and it's fast for lots of stuff. But if you need to, do some quick calculations, send it to the GPU, have it done there quickly, and come back and hope that the bottleneck of getting memory in and out of this bus is, well, let me say that the GPU speed up is large enough that bottleneck doesn't cost you too much, that it's actually still faster to do that. And that's what actually, that's basically the hard thing. Now in GR we're a little bit, we have one thing working for us and one thing I think against us, and that is our computations, say in relativistic fluid dynamics, are they're significantly more difficult, or there are more flops involved than, say, Newtonian fluid mechanics. The other side of that is we have many more fields that we have to move around, if you're trying to follow this model. I talked about needing, in that first quote, it said basically we need new algorithms and new ways to do things. That's basically, looking at this hardware limitations and trying to figure out how best to exploit it. If you've ever written, compiled your code for, an Intel Phi and ran it, you were most likely disappointed. If you did nothing else but just turn on some compile flags, you probably saw like a 10% penalty or something. That's not uncommon. That's basically telling us, to really use these efficiently, the programmer is going to have to do a little bit more work. What we've chosen to do is to look at, there's basically OpenCL, which is kind of a general language for doing this. We've chosen to work directly with CUDA because it's NVIDIA's API or language that allows you to program for the GPU. It's very extensive and it allows us very fine control over the memory. Remember, there's not a lot of cache on these things, and so exactly the way things are arranged in memory will depend, greatly affect the efficiency. OpenCL doesn't yet allow us to tune that to the level that we need to. I don't know if you can read this or not, but this is basically just kind of showing you that in standard C code you would write a loop that multiplies A times X plus Y and with this little subroutine, and you call it this way. The big difference here is in CUDA, there's no for loop. We just have variables that count essentially, which thread I'm on. All these little GPUs are arranged by blocks and threads, and and you just say, okay, where am I? That's going to be my index number, and then I call it with a special notation here that tells the GPU how to divide up the code. Well, in looking at this, as CUDA has great, as there's many capabilities have been added over recent years. One nice one is the ability to work with MPI directly on the GPU, and that's motivated the strategy that we are trying now. As I said, the standard model was to have all your code here on application. So blue means it's running on the CPU, green means it's running on the GPU. So your code is mostly on the CPU. You kick something off to the GPU really fast, and then you continue on the CPU. We've decided basically to turn this around. Now that we can use MPI directly to communicate between GPUs, don't go through the bus if you don't have to. Put everything on the GPU. Let it run there. That way we don't hit this bottleneck performance penalty. And GPUs talk directly to one another, so I don't have to go through the bus to the CPU to communicate. There's still some external communication, but I'm avoiding the CPU in that route. And basically, as I said, turn this around. Run everything on the GPU. If I need to do I/O has to go through the CPU, so I'll do that. Send it to the CPU to do I/O. It can be done asynchronously to keep the GPU hopefully running and computing, and then stay on the GPU so I don't have the bottleneck performance hit.
So it's a good model when you don't require a lot of RAM for the GPUs, right?
Well, we need a lot of RAM, and the K20 has I think 6 gigabytes of RAM per K20, and we think that we can, with 600 available on Big Red 2, that we'll be able to put our codes on those. So by using memory very carefully, I think that we'll be able to do that. This still is, I wish I had more, we were further along, but it's something that we've just been working on recently. We have written a quick little code that evolves the vacuum BSSN equations. It's kind of a first go. And we wrote a version that runs on the GPU and communicates through the GPU with MPI, and a version that runs on the CPU. So this is in our production code, which is much bigger and has all the bells and whistles and too many flags that who knows what they do anymore. But this is kind of a stripped down version, so that I'm comparing kind of as close as I can apples to apples here. The red line shows this is simply runtime to run a job of a fixed size. So this is strong scaling. The red line is the CPU code. The blue line is the GPU code, and up to with the GPUs up to 16 GPUs. And we have, a nice on one processor almost the factor of 100 there, and out on 16, and just total runtime, say a factor of 10 improvement by running on the GPU.
So what do you mean by you have 16 GPUs? You mean you have 16 GPU cards, or you mean you have using
16 GPU cards.
Okay, and how many?
So that's actually 16 nodes. On Big Red 2, there's only one GPU per node, and so it's running on 16 nodes.
So you're not getting an enormous speed up when you go from one node upward, and probably that there's a big networking bottleneck. Instead of going off the bus, between the CPU, you're going off the entire node basically.
Yeah.
And that's probably what's explained.
Yeah.
But still, it's quite a high speed.
Yeah. And there's a lot of tuning that we hope to do, especially with that communication. So this was done before we were working with the, we have the asynchronous I/O now going. This is done with no I/O turned on, but the asynchronous MPI is something that we haven't put in yet. And we hope to eliminate some of this, or push this down with more GPUs as we have the asynchronous MPI.
Will this strategy still be relevant when unified RAM is available? So CPUs and GPUs can both fetch from the same RAM?
Yes. I mean, if it's on the same RAM, then maybe we can do more on the CPU. But as far as using the GPU as an important device for doing the floating point calculations, yes, I think it will. It may make it easier to, to put different parts of the code in one place or the other. But the basic idea is that no matter, we're not sure if this is going to solve all the problems the big problems that we see right now with our code in doing the very long runs, like with the Kelvin-Helmholtz instability. But our hope is that, our thinking is that even if this, if technology doesn't turn out to be the thing in of the future, something like it will. Whether you're programming for the GPU or for an Intel Phi or whatever comes after them. The basic idea of having specialized hardware for these lightweight threads is going to be the future.
This graph is only for backup spacetimes right?
That's right. That is correct. There's no hydro yet.
You
Yeah.
plan to use it for the Kelvin Frankfurt, so
We're writing a. Yeah, this is something that we've mostly been working on over the past few months. It's very.
Do you think there's going to be a significant change in how the graph looks like?
I think that the hydro will not scale maybe quite as well as the BSSN. In some ways, BSSN is a very simple, from a computational standpoint. I can imagine writing my right-hand side as one great big loop, and I figure out how to put that on the cards. Where hydro is, there's basically I have a part of it that's calculating source terms, and then I have also a more complicated reconstruction procedure, which is not as simple as a finite difference. And then I have other parts that don't scale well. So the calculation of primitive variables is something that does not scale as well on a GPU. And the reason is GPUs are very fast. They're streaming processors. If they're all doing the exact same thing, they're very fast. If at some point there's logic that says this processor needs to do something else and this one's going to do something else, then the parallelism is broken and it goes through and executes them serially. So that's a challenge as far as writing your primitive solver. So you can probably fix that up by trying to eliminate as much logic as possible and do as many calculations before you check things, so that you maximize calculations versus the number of times you check for convergence or something. But it's overall something that's not ideal for a GPU. And maybe when we have the unified memory, then pushing that to the CPU would be a better thing.
The space-time in GPUs and the hydro in CPUs or something like this?
Yeah, if there were a unified memory, then certainly you could do that. We're trying to avoid that, at least for now, because of the bottleneck of communicating between the GPU and the CPU. But okay, yeah, that's. Oh, I just have one last topic. That was binary neutron stars and the origin of life. I only thought about it since last night. I was going to try to, get my Photoshop skills here and show, like the primordial soup stirred by binary neutron stars, but it didn't quite work out. So anyway, maybe for the published version of the slides, we'll see. Anyway, that's the end.
More questions?
I know you're mainly focused on GPUs, but what about these Intel Phi coprocessors that you mentioned? Do you know how difficult it is to port your code into these?
So I haven't looked as closely into the Intel Phis. I have done the, try to compile, turn on the compilation flags to use the Intel Phi. And on one particular problem, I was able to get like about a 20% speed up. It wasn't a fluid code; it was a post-Newtonian code I've been looking at. But I haven't. You quickly get to the point where you realize, okay, at least what I found, if you just hand things to the compiler and hope that it does the right thing, it's not going to. And as I looked into, okay, how do I get more than this 10%, 20% speed up on this post-Newtonian code? I quickly find out, well, I've got to write in, what is it? Some language. I don't remember the name of the language that you have to write in. But it quickly becomes, essentially writing something like in CUDA. And yeah, that's what people tell me, and because the Intel Phi has the kind of the same basic chipset as the CPU, but just turning it on naively doesn't give a very much speed up. Not what's promised anyway. Even on my laptop with my small little graphics card in here, I run a test for reconstruction, PPM reconstruction, and I get a factor of 2 speed up just using the GPU, which is better than the 20% say I've seen on an Intel Phi. And that's not tuned in any way, just naive anyway.
Can you go back to the Kelvin-Helmholtz curve that you...
Mm-hmm. This one or the...
So do you think you are resolving the Kelvin-Helmholtz with the red or not?
No.
So,
and I don't even think even with the green. And
okay. So then this is telling that whatever growth you see between 1 and 2 milliseconds after the merger or after the OU start, that's just the compression.
Yeah.
Flux conservation. So then the Kelvin-Helmholtz doesn't really give you 1 order of magnitude. It's going to be...
That's right, yeah. Yeah, I said that wrong. Mm-hmm.
Because you're really getting 1 order
Yeah.
of magnitude just from the compression.
Yeah.
So Kenta, do you have an estimate how can you distinguish what is the growth due to the compression, flux freezing, and the one coming from the instability by just looking at where you quench the instability because you don't have enough resolution?
I have not checked.
I think that would be a very interesting measure because that tells you how effective the instability is in boosting your magnetic field.
Mm-hmm.
I'm not checked.
Okay. Any other questions or?
So, what is the typical, when you run, this run, for instance, how many, and you compare with the scaling that you are seeing on the other slide, how many cores or nodes would you need there?
I
so
do.
You have a blue curve and a red
Yeah.
curve, okay? And the blue curve is almost constant, so that if that doesn't change, not here, I mean in the other slide,
Yeah.
two will cross. Where is the crossing? Is this,
I'm not sure.
Uh-huh.
That's a good question. You're talking about the comparison with the GPU scaling?
Yeah, if you go to that slide.
Yeah.
And you assume that pessimistic view that the blue just doesn't improve. At one point, the blue and the red will cross.
Yeah.
And what is that number? Are you looking at 10,000 cores or 1,000?
Yeah, I assume. I'm not sure. Come over here. But you're really limited with memory. What you can do here with, and as far as thinking of the Kelvin-Helmholtz problem.
But this is not a fair comparison because when you do this is strong scaling.
Mm-hmm.
So you don't change the size of the problem.
Yeah.
And therefore, the one which is much cheaper scales much worse. This is what you usually get. If it is a cheap problem, then it scales very bad. If it is a very expensive problem, it scales perfectly. But the interesting thing would be to see the weak scaling. And probably it will scale very nice. But
Yeah.
I think this is perfectly normal.
Yeah.
This
Yeah.
just means that that you are doing it much better for this one. I would say.
Mm-hmm.
Well, I still don't understand that comment, but because the blue and the red are showing you the same text. Okay, so the red is saying that as you increase the number of processes, the execution time goes down. So never mind the 64 point, but if you stick a 16, I think they are logically equivalent, and they are telling you that you have this speed up of a factor, I don't know, 1,000 or 100, but they are doing exactly the same logical thing.
Yes, but I mean, if you have 100 times less work per node, then it will scale much worse than
On the GPUs, if you don't keep the threads busy, then you won't get any scaling. So it's possible that you just basically got cores on the GPU not doing anything once you get to this.
So, for example, if you were to increase the load in the second case by a factor 100, I guess you should get the same scaling, because you are just limited by the communication, which should be very similar.
The blue curve is network limited. The red curve is CPU limited, which is why you get
Exactly.
pretty good scaling as you increase the number.
So if you go down the red line to the same limit, it will saturate in the same
It
way.
will, absolutely.
So you have to compare with scaling. This is a bit misleading.
Yeah, I think this was done on just 99 cube points, and so obviously out here the GPU is with 2,000 cores is not doing a lot when you have 16 of them.
Maybe you have 1 point per core. I don't know.
Yeah.
Well, if there are no other questions, when should we resume at 4? So we'll take a tea break for about 10-15 minutes and then meet our cookies upstairs.
Yes.
Okay.
Let's thank everyone.
Thank you.